Yes. Okay, perfect. So good afternoon, everyone. So first of all, let me thank the organizer for having me in this great conference. I am Martina Donnari, and I am a postdoc at MPA in Heidelberg, and I am collaborating with Annalisa Pillevic and the TNG team. So today I'm going to present the role of the environment and preprocessing in the IllustrisTNG simulation. So this is the motivation of the talk. So today I'm going to present different effects of the preprocessing in the galaxy evolution. So the first question that I want to answer, and basically I want to show you the first evidence of chemical preprocessing in the cluster formation history. And then I'll show you the quench fraction, and particularly how, what is the role of preprocessing in quenching galaxies prior to their accretion into the redshift zero host. So the tool that I'm going to use is the IllustrisTNG simulations, which is a set of 3 different cosmological-hydrodynamical simulations. And today I'm going to present results from TNG 300 and TNG 100. So just to have in mind what kind of numbers are we using. So we select all galaxies with the stellar mass larger than 10 to the 9 solar masses, orbiting in groups and clusters larger than 10 to the 13 solar masses. So let me start with this movie, which is showing you the stellar distribution of a forming cluster at redshift below 1 in TNG 50. And as you can see, while the cluster is forming, we can see stellar stream, we can see tidal tails, merging galaxies, and we can also see some galaxies that infall into the main body of the clusters. And so we can say that, of course, the cluster assembly has an impact of both their evolution, but also on the evolution of their satellites. So basically with this simulation, we can follow the evolution of galaxies, and we can go back to their infall into the cluster. And so just let's do it. So the first result that I want to show you is a paper of Gupta in 2018. They used the TNG 100 sample, and they basically divided their cluster their galaxies in a cluster galaxy sample, meaning that they select all galaxies in between 10 to the 9 and 10 to the 10.5 solar masses, orbiting in groups larger than 10 to the 13 solar masses. And then they subdivided this sample into accreted galaxies, meaning that the redshift of infall is higher than the redshift of the observation, and the opposite for infalling galaxies. And then we have the filled galaxy sample, meaning that the mass range is the same, between 10 to the 9 and 10 to the 10.5, but they are orbiting in OS less than 10 to the 12 solar masses. So just bear in mind the colors. So green for infalling, red for accreted galaxies, and blue for filled galaxies. On the left-hand side, you can see the star formation rate weighted gas phase metallicity only for galaxies with a star formation larger than 0 as a function of galaxy stellar mass for 6 different redshift. And the first thing that we can see is that at redshift 1.5, we can already see an emergence of environmental dependence of metallicity, meaning that, especially at redshift below 1, the accreted galaxies, so red points, show a metallicity enhancement up to 0.2 dex with respect to the field. But most important is that if you just look at the green points, so the infalling galaxies, they lie always between accreted and filled galaxies. And we can talk about a chemical preprocessing of these infalling galaxies, because I want to remind you that these galaxies, these infalling galaxies, are not yet part of the cluster, but they are orbiting outside 2 times R200. Indeed, if we just have a look on the mean metallicity of the inflowing gas, you can see that the infalling galaxies, which are these red points here, are accreted at least 1.5 or 2 times more metal-rich gas compared to the filled ones. And so we can actually see that the rich gas inflows can be important and significant at distance larger than 2 times R200. In this case, when I'm talking about preprocessing, I'm talking about, I'm broadly speaking, because I'm talking about a modification of the properties of galaxies prior to the infall into the main cluster, but they are completely irrespective of their prior group membership. So if we just have a look on the role of this prior group, we can just observe the quench fraction. So here I'm showing you the quench fraction and their dependence on the stellar mass, redshift, cluster-centric distance, and time since infall. So here we can basically divide the main result into subgroups. So the first one is for low mass galaxies, and meaning for galaxies with stellar mass less than 10 to the 10.5, 10 to the 11 solar masses. And we can actually see that if they are not satellites, so for central galaxies, for low mass central galaxies, they are rarely quenched. And this is in line with the environmental driven quenching scenario. Overall, we can see that the quench fraction is lower at higher redshift. And for satellites close to their center here and early infallers here, they are more likely to be quenched. But if we just have a look on high mass satellites, so for stellar mass larger than 10 to the 10.5, 10 to the 11, we can see that the quench fraction is always 80–90%, regardless of redshift, as you can see here, the cluster-centric distance, or the time since infall. Meaning that these massive galaxies can quench basically on their own, without the effect of the environment. This means that they are quenching because they're secular internal processes. That in TNG is mainly the AGN feedback. Of course, the quench fraction is depending also on the host mass. So here on the left-hand side, you have the quench fraction as a function of galaxy stellar mass for galaxies being in the 4 host mass. And on the right-hand side, the quench fraction as a function of host mass being in different galaxy stellar mass. So overall, the main result is that the quench fraction is always higher in clusters than in groups, meaning that the clusters are more efficient in quenching their member. But again, if you are just looking at the high mass send, you can see that for galaxies larger than 10 to the 10.5, we have always a 90–100% of quenched galaxies. And again, this is mostly due to internal processes. But just have a look on the role of this preprocessing. So here on the left-hand side, we have a simple scheme that explains you how a galaxy can become a satellite. Of course, this is a simplified word, but you can see that, for example, if you just follow the purple galaxy, you can see that this is falling as centrals, meaning that it is directly accreted into the main branch of the redshift 0 host. On the other hand, we have the green galaxy, which is a galaxy that fall as satellites, as pre-processed satellites. So these galaxies first fall into a small subgroup, which in turn will merge in the final redshift 0 host. So if you just ask if the fraction of redshift 0 pre-processed satellites is a function of galaxy stellar mass and host mass, the answer is basically yes. Because here you can see that we have roughly 50% of massive satellites that are found today in high mass cluster have been preprocessed. And of course, this is due to basically for the hierarchical growth of structures. Of course, when a galaxy becomes quenched, it can follow diverse pathways. And so, for example, if we just select the whole quenched satellites at redshift 0, we can split up this group into small subgroups, which are quenched as centrals, meaning that they are quenched before the infall, or quenched as satellites. But in this latter case, again, you can split up these groups in quench as preprocessed satellites, so they are quenching in small subgroup, or they are quenching in the redshift 0 host when we observe it day to day. Of course, in this latter case, this does not mean that a satellite has not been pre-massaged, let's say, in some sense. So it could be that it previously orbited in other groups. So even if a galaxy can quench in the redshift 0 host, the star formation activity can be also altered in some sense during the preprocessing. If we just make a step back and we turn into the quench fraction as a function of galaxy stellar mass, again for, yes, got it. As a function of galaxy stellar mass for different host mass beams, so the dashed line are the plot that I showed you before, and the solid line is the same plot, but after excluding all satellites that quench before their last infall. And so basically you can see that again, for low mass galaxies, we have the ranking ghost is preserved. So the more massive clusters are indeed more efficient at quenching their satellites. But for high mass satellites, and for high mass galaxies, we can say that we have an inversion of this trend, mainly due again to the AGN feedback. So the main culprit of their quenching is internal process that in TNG is mainly the AGN feedback. So the last thing that I want to show you is the distribution of the mass quenching and the time since quenching. So you can see here the three subgroups that I showed you before. And you can see here that if a galaxy quenches satellites, it can basically quench in between 1 and 8 gigayear ago, depending if they quench as per process satellites or if they quench in the redshift 0 host. But if a galaxy quenches centrals, this is only true for massive satellites, and they can quench in between 6 to 10 gigayears ago in hosts of in between 10 to the 12 and 10 to the 12.6. So this brings to my conclusion. The main take home is that, of course, the study of the assembly history is fundamental for understanding the properties of galaxies. I showed you that we can talk about chemical preprocessing that emerged already at redshift 0 in TNG. And we can also see that the environmental processing in hosts most massive than 10 to the 13th solar masses is already in place at redshift in between 1 and 3. And thank you.